All right. So here we are, everybody. Assignment 9, the last assignment for this semester's 302 class. We finally made it. So this assignment is going to be a graph theory program, and of course you can ignore this first paragraph. This is just, I don't know, seems like me just kind of ranting at the frustrations of Resident Evil 3. But when you first play that game, it's frustrating because it's kind of tough to beat that game with all the puzzles and so forth. But then the ultimate, best feeling is when you finally beat Resident Evil 3. All that hard work paid off. So basically, in this story, in this game, essentially, you're going to have a map of the Raccoon City Police Department, which is a classic sort of section of Raccoon City, which was played in both Resident Evil 2 and Resident Evil 3. And I guess Leon is going to be trying to escape, and Nemesis is chasing after him, which makes not much sense really. But of course, Nemesis is definitely the much more cooler villain than Mr. X, and there's no arguing that, of course. So basically, as any Resident Evil game you ever played, it's all about finding keys to open up rooms and escaping. So you're gonna have a map of the police station, and then what's gonna happen, you're gonna have to find keys to open up new doors, and you want to eventually find that secret sort of entrance to get out of the Raccoon City Police Department, so then you won't be trapped with Nemesis inside, and that would definitely not work out well for Leon. So basically, what's going to happen is in this program you'll be given sort of an input file with the map, which is going to be your adjacency list in a sense. Well, not really adjacency list. It's going to be just a list of edges, and you're going to create an adjacency list out of it. And then once you find a room with the key, you're going to have to insert or create a new edge into your graph, because a new edge means a new door is openable. So think of it where each node is going to be a room and an edge is going to be a door between two rooms. And initially this will be a disconnected graph because some rooms can't be reached, but then when you find keys, you're going to insert edges into your graph, which is going to allow you to maneuver through the rest of the police station. So let's first go over our adjacency list. All right. So basically, we're going to be using this array of linked list structure, but we're going to keep it hidden within this adjacency list. So pretty much, I'm going to, let's see, what should I talk about first? Well, I guess the first thing is, we're going to have a struct node. So we're going to have a linked list structure. So every node in the linked list will have an item and a link. The item is going to be sort of the node ID of sort of an edge. So remember, when you have an adjacency list, you have sort of node A goes to node B. So the item will be your node B essentially. I guess when we go over the class adjacency list, it'll make more sense in a second. So let's go ahead and just go over the vertex class first. So the constructor, so we have this node star neighbors, and that's going to be your head pointer for a linked list. So a vertex object is going to be a linked list, and you're going to have an array of vertex objects. So what's going to happen here is you're going to have this constructor, vertex constructor, is going to just basically set neighbors to null. Nothing fancy there. The copy constructor, well, that's going to do a deep copy, and this might not really be used, or actually it could be used when you're doing your content, but really not hard to write the copy constructor. You just do a deep copy of a linked list. It's a singly linked list, so really I can't imagine anything too bad. You can, of course, sort of use add edge within the copy constructor, sort of. So you can do that, but you have to sort of copy a linked list. So the object being passed in, it's going to have a neighbors pointer, so you have to iterate through that copy object's linked list, and just one by one insert them into the left-hand side linked list. I mean, I don't know how much clearer to make this. I mean, it's really nothing too new there. Then the assignment operator, I mean, yeah, you pass in the right-hand side object. So you're going to have the this arrow neighbors, RHS.neighbors, and you simply just do a deep copy of a linked list from right-hand side into your this object. I mean, just a standard deep copy of a linked list, nothing very fancy there. Then you're going to have your destructor, which is going to deallocate your whole linked list. Yeah. Then we have our add edge function, which you're going to pass in some parameter of type, and you're going to simply do a head insert into your linked list. Now it could be a tail insert, but add edge is going to add a node into adjacency list, and I guess a head insert is a bit more efficient because head insert is a constant operation, whereas if you were to do a tail insert, you have to traverse the whole linked list first and insert to the end, which could take more time. And it doesn't really matter what order you have your neighbors list, as long as all your neighbors are in the linked list, you're okay. And then you're going to have, obviously, an edge iterator class, very similar to our first assignment. So we have edge iterator, which is going to be our pointer essentially, or kind of our beefed up, steroided up pointer. So this edge iterator is going to iterate through a linked list. So, we have this node star current. So the constructor sets current to null. Edge iterator node star sets this pointer equal to current. Operator plus plus is going to be that postfix operator. It's going to move current over to next element. Operator star returns current arrow item. Equals equals not equals. Just we compare the whatever iterator object we're passing in and compare that current to this current. If they're equal, return true, else return false, and not equal is the opposite of that. And then for the begin and end, the begin function returns an iterator whose current contains neighbors. So, very similar to the begin function from assignment 1. And the end function returns just, it's going to return basically, I guess I had to return a null, although maybe having it return, it returns a null basically. So it returns that end node, so which can be used to traverse through your linked list. So basically, vertex is just a linked list. That's all it is, a singly linked list. And then edge iterator is going to be your iterator, which is going to be that beefed up pointer, which will allow you to traverse through your linked list, when you're trying to do your sort of traversals in main. So all the writing is over here, so I don't know. Seems like there's not much to say about this. I really hope this is not a major problem. So for this assignment, you're going to have to actually use a hash map class. Now, once again, not once again, but just to kind of make this clear, if you can't get hash map to work for this assignment, which could be the case, hash map is a very bizarre class. I had students, it worked fine on their earlier assignments, and for some reason on the newer one does not work. So, one trick you can do is, if the resize function gives you problems, you can, of course, in your constructor for hash map, you can, of course, just maybe set the size to be 100, so it won't have to do a resize. So if, let's say, your hash map overall still works, then I guess, I'm trying to really give you extra credit points for this assignment. I really am trying my best. So if your resize has problems, you can, of course, try setting your table size to like 100, of course. But either way, you can use unordered map if you want, which is fine, but you will not get extra credit points if you use that, though. So it's up to you. So there's that. So the reason why we're using an unordered map is because, well, for our examples in class, when we did any graph theory traversals, we always use indices like 0, node 1, node 2. But in this example, the graph, each node is going to have a name, a room name. So a room in the police station for the Raccoon City Police Department. So you're going to actually have to use strings as the node names. So the indices of your adjacency list is going to be a string, not an integer like you do for our examples in class. So basically, you want to have this structure set up, but the real details are going to be here in the contents of main. So you're going to be given two input files. One file is going to just contain all of the edges, and obviously we're going to be using a directed graph, but we're going to really implement an undirected graph. So for example, if you have the following edge in our file, so in our map file, every line will just contain a string separated by a space, then another string, and every line ends with a new line. So this means that main hall has a door from main hall to waiting room. And also, there's going to be a door from waiting room to main hall. So you're going to have in your adjacency list, you want to make sure that main hall, its outgoing neighbor will be waiting room, and waiting room's outgoing neighbor will be main hall. So that's going to be how you can sort of think about this. So you're going to have the following structure. I guess I showed either one. So here's the complication. So I guess I'll use unordered map, I suppose, because this one for sure is going to work. So basically, the way this map is going to work is you're going to have a string that's going to be sort of a room name. And this string maps to a vertex object. And a vertex object is going to be your linked list / adjacency list. So that means a room name maps to a list of neighbors. And I'll sort of paraphrase this as I go through this video. Well, I guess I'm going to paraphrase it right now since it's right here, the very next portion. So suppose main hall has an edge that goes from main hall to waiting room. Then obviously using our map object, I would say map, and then main hall is going to be my array index because it's going to be a hash map, dot add edge waiting room. So that means that, okay, there's going to be an edge or open door from main hall to waiting room. If main hall had other rooms, of course you just use map and then the string name, the room name, and then dot add edge means I'm going to have a door that opens this room to this room. And of course, you also want to make sure you have map waiting room dot add edge main hall as well, because it's going to be a two-way sort of graph basically. So you want to make sure that you want to have every single case covered. So because it's going to be really going to be undirected graph, but we're going to be using a directed sort of adjacency list to really kind of emulate an undirected graph. So I guess, typo right there. Yes. Well, you know what? I think you knew this is supposed to be vertex. I'm not gonna fix that. So it's supposed to be vertex, as you can imagine. So it's not the end of the world if there's a typo right there. It doesn't affect the actual code grade at all. It doesn't affect anything. It's just a typo. So yeah, typo, vertex, whatever. So basically, what you want to do is you want to one by one read this file. So let me make sure I open up the right file. So I'm going to actually go to my assignment 9. I'm going to make sure that I open up the right files. Let's go ahead and let's see. I don't open the source file. Open this up right there. That would make this program not so much fun for you because it would give away the answer. So let me go ahead and say police station. I'm going to open up this one. This is actually the original file I went with, so it's police station OG. So it's going to be the original file I use. I actually scrambled these up in our input file, but you can see here that every line will contain just a pair of these names. Also, if you look at the one I gave you, it's kind of scrambled up so that way you can't make assumptions in your code. You can't, so it's a bit more randomized. But I'll go to this file for a second. We have main hall and then information office. So you want to go to map and then bracket operator, the string main hall dot add edge information office. And also you want to do map and then bracket information office dot add edge main hall. So it's a two-way sort of edge. And you go through one by one each line. It's going to be just simply A goes to B and also A goes to B. So basically you want to make sure we add those two edges in. So that's all you're going to do is just create this adjacency list. And a hash map is a perfect method of being able to use strings as quote unquote array indices. If hopefully that makes sense. So you want to build your adjacency list. And of course, if you want to traverse through all the neighbors, so when you're doing your depth first search type traversal, you want to go ahead and use this loop right here, which is going to essentially iterate through all of your neighbors. So IT is going to be an edge iterator, and then set equal to adjacency list. It's supposed to be map. I think I used my last semester's write-up right there. It's supposed to be map, but it doesn't really matter. So that's supposed to be map. So just just FYI. So this is going to set the first neighbor of main hall in IT, and we're going to basically just I put map over there. Wow, I mean I must have really been not focusing. It's okay. It's been a long semester, so I think I'm mentally just worn out, so I can't focus anymore. But anyway, this is supposed to be map right here, and this IT is going to iterate through all of main hall's neighbors. So for any neighbor, just plug in the vertex name right there, and this is going to essentially iterate through all the neighbors, and star IT is going to return a neighbor. So for example, main hall has two neighbors, information office and waiting room. So when I say star IT, it's going to actually return a string, which is one of the main hall's neighbors. So star IT will return this string information office, and then if I do IT++ and star IT, it will return waiting room next. Or vice versa. I mean, maybe it's, I don't know what order it inserted these into our adjacency list, but you get the idea. So just sort of a using iterator method of being able to traverse through all the neighbors of a node. So that's going to be your first task. Your second task is going to be, well, you're going to want to store. So your next file you're going to be given actually is going to be your keys file. Let me go ahead and close this file right here. I'm going to go through playthrough a.txt. So of course you had different playthroughs Resident Evil. I think Resident Evil 3 didn't really have different playthroughs. Resident Evil 2 had I think 2 playthroughs. This will have a 3 playthrough game. So what this represents is that, well, this means that in the interrogation room, we found a key that opens up the door that connects these two rooms. File storage has a key that opens up the door between these two rooms. So you'd have to add this edge into your adjacency list. So you have to have main hall has an edge from main hall to payphone corridor, and also you have to add an edge that has a payphone corridor goes to main hall as well. Watchman's room has a key that goes to dark room to exit. So exit is going to be the winning ticket. So if you can find a path to exit, then you were able to escape the police department. And of course, operation room has a key that connects these two rooms together. So let's go ahead and draw. I have sort of the predefined graph over here. Now this is going to be kind of not so nice handwriting, but just kind of bear with me on this. So right now, here's going to be our sort of graph. Now those edges that are in blue, this is I think violet, red, and green, are not originally going to be in my graph. But these edges are going to be added in when we go ahead and we find different paths. So based on this file we have right here, interrogation room has a key that opens up winding corridor and operations room. So I'm going to go ahead and mark them here on this map. So interrogation room is right over there. I'm sorry about my very terrible handwriting. I kind of wrote this pretty quick. So this one has a key, winding corridor and operation room. So this one's going to have, I guess, a violet key. I'm going to color code this. So if we enter this room, we found a key that would open up this door. So this violet arrows mean that it's not part of my graph, but we're going to add this edge, or these two edges, into my graph once I enter this interrogation room. Now file storage is going to have a blue key, which would actually open up the door between main hall and payphone corridor. Then watchman's room, so watchman's room is going to have a red key, which is going to be the key that unlocks dark room and exit. So apparently some secret door, I guess, in the dark room. I think dark room has like this really weird, that weird sort of room where those, the actual dark room, I guess, if you will, next to the typewriter. So I guess that's where the secret exit would be in this police station. Sure, why not? An operation room has the following. It's going to have a green key, I believe. This room opens up the door between main office and basement stairway. So that's going to be the idea. So you're not going to add these edges in right away. You're going to add these in once you actually discover a room that has a key in it. So let's go ahead and go back to the write-up, and I'll go ahead and I'll sort of draw this out, or sort of give you an idea of what you have to do. So let's go back to the PDF. You want to use either this or this structure to maintain this. So an unordered map, string, vector string keys, this structure is going to maintain essentially this. So you're going to have the following. This is going to be your key, and a vector associated, so interrogation room is going to be your key type for unordered map, and this is going to be your vector of 2 strings. So this structure, the bracket operator returns a vector. So if I went ahead and said keys at index bracket operator interrogation room, I wanted to do a pushback winding corridor and then pushback operation room. So if you were to construct this, you would just, actually I put it right here, actually I put that right here literally for you. So keys file storage pushback main hall, and then keys file storage pushback payphone corridor. So then when you enter a file storage, you know exactly the 2 rooms that are connected, because if I go to, wow, I put this here in a PDF. Wow, I actually gave you a lot of, so okay, fine. You know what? That one typo I had, this really makes up for that typo right here, because I gave you really a lot of help. So if I have keys, file storage 0 contains main hall, and then keys, file storage 1 contains payphone corridor. So that way we can very quickly if we enter a room, we can quickly see. So basically the idea is that if, let's say, I enter this room, for example, payphone corridor, there's no room, there's no key in this room. So what happens if I went ahead and said keys, payphone corridor, it would be an empty vector associated with it, correct? Because your hash map is going to set a blank T2 object to the value field. So so basically if keys, whatever string you use, dot size or dot empty, that means there's no key in that room. Hopefully that makes sense, but I'll just say it again. So if, let's say, keys, and you pass in some string, dot, so keys, some string, dot empty, if that's true, that means there's no key in that room. Pretty nifty. It's cool how hash maps just kind of work like that. So the real complication is going to be you want to implement this function right here. So I'm going to go ahead and just pause the video. I'm going to do a sort of I don't know, is that a break or a cut or mode? I don't know what it's called. I'm going to do it right now just so I can kind of make sure I can compose myself so I don't make a mistake on this part. Okay, so I'm at my checkpoint. So if I make a mistake right here, I don't have to record the entire video. So, okay. So this is going to be your depth first search traversal. And you may have to call depth first search more than one time in your program. So basically the first thing you're going to do is in main, you're going to call depth first search. You're going to pass in your map. You're going to pass in your keys vector, visited. So it's going to be another hash map you're going to use. Now, of course, you can use also unordered map instead if you want. I just put hash map there, but of course you can change that if you want to that. So this is going to be your visited array, but once again, remember we're going to map a string to a boolean. So we're going to map if a room name has been visited, yes or no, true or false. So same idea, just we're using a string as our array index. So the first idea is when we first call this function in main, we're going to, of course, for our cur, it's going to be main hall. Of course, we always start from the main hall whenever we enter the police station, any Resident Evil game. I think in the remake Resident Evil 3, I'm not sure if you started off there. Well, even in the remake Resident Evil 3, when you had Carlos, you actually do enter the main hall first. So you always start from the main hall. That's kind of I guess, almost an axiom in Resident Evil. You start from the main hall. Okay, so here's how you want to actually implement this structure. So I'm going to go back to my notes over here, and we're going to currently, let me see, what can I'm going to use, let's see, I already used so many different colors here, so, okay, I'm going to maybe add a new pen. Let's add Is there a yellow? Can I put yellow in here? That would distinguish with the rest, I think. Let's try yellow. That's not yellow. Okay, you know what? I'm just gonna go with this color. I don't know what this is. That's not a good color to use. Okay, now I'm kind of stumbling here. I mean, I should stop the video now. Okay, you know what? I'm just gonna go ahead and just I want to use gold. Gold's a good color. Gold's good. So we're gonna start from main hall initially first, like that. And of course, well, we have that blue edge right there, but it really isn't sort of opened yet. So in main hall, what would happen is, well, I mean, there's two paths we can take. Let's go ahead and make this easier on ourselves, but obviously that first search could take any path. But let's say it happens to go to waiting room first. Goes over here. There's no key in this room because if I went ahead and passed in waiting room into my keys hash map, it would return empty vector. So that means there's no keys there. We'll jump over here. Nothing here either. And just to make things simple, that first search will jump over here. And it found a key in this room. So because of that, we're going to actually add this edge into my graph. Because now we opened up a room. Now, of course, you have to find that door because, of course, in Resident Evil, you can't really know which door it actually opens. You know you found a key, so you gotta go ahead and try to see, well, what door does that key open? So when you do this, what I did in my implementation is I would go ahead and return the string file storage. So I'm going to return, I'm going to put it as fs for right now. It returns fs, it will relay that all the way back to main. So I call the function in main, I pass in main hall, it returns back file storage. Okay, so that means I found a sort of a key. So at this point, I would have to check. So what I would do in main actually is I go to keys, index file storage, and I would add the edge actually in main instead. Because I'm not passing the adjacency list by reference into the function, although I could, but I did not. So actually when I return back to main, and the function running, it returns a string. So in this case, if it returns file storage back in main, that means, okay, I found some type of a room that opens something up. So what's going to happen is I sort of, add this edge into my graph. I'm going to make sure I kind of unmark this. So maybe remove that vector. So that keys at index file storage dot clear. I want to clear this vector out. I want to sort of, this key is no longer in this room because I just simply walked into that room. I picked up this key. So this key is not in the room anymore. So I want to make sure I clear that out. And what I would do next is I would go ahead and now I'm going to call DFS again. But this time I'm going to start from file storage. So basically what happened was Leon entered his room. He found a key. Okay, cool. I found a key. Awesome. So I'm going to do DFS again. But now I'm going to start from file storage this time. And it's very simple to do that because all you have to do, just kind of brace yourselves for the bright light. I'm going to pass in for cur, I'm going to pass in file storage. So then this DFS running function is going to basically start from file storage. And also make sure you unmark all of your visited, unmark them all to be false. Or you can sort of reallocate a new visited object. Or maybe even declare this object in a loop. So it's going to kind of redeclare every time the loop iterates. Hint, hint. So what's going to happen is we're going to call DFS from file storage. And of course, we're going to traverse this graph. So we're going to take this edge to L corridor, to winding corridor, west stairway. Maybe go actually to dark room, let's say. And dark room hits sort of a dead end. So what's going to happen on a dead end is going to return back an empty string. So empty string being returned back, only thing that means is that the path from west stairway to dark room led nowhere, so we're going to try a different path. So if we call DFS on a neighbor and returns back an empty string, that means, okay, then let's try a different path. Let's try this path over here, information office. We tried this. Let's say we went over here to evidence room. A dead end happens. It returns back an empty string, which means, okay, information office, if it went to evidence room, there's nothing to see there, so we'll try a different path. Okay, let's try main hall next. Then from main hall, I'm going to go ahead and try payphone corridor. Payphone corridor would try maybe main office, and main office has nowhere to go because that edge is green, but we haven't really opened this door yet. We haven't added this edge into my graph just yet because, well, there is no path. There is no edge just yet. We have to find that room with a key that can open that room. So it returns back empty string. So it tries a different path. So then it's going to try interrogation room next. Then it's going to try, interrogation corridor next, my mistake. Then it will try interrogation room. And right there in that room, we see we have a key. So every time we enter a room, we're going to check that key's hash map. So keys, at the index, we're going to use the room we're currently in. If that vector that's associated with that is not empty, that means that room has to have a key. If it's empty, okay, well then that room has no key, so you have to keep doing depth first search. So here we found a key. So now we're going to have to return back. I'm going to return, I guess, interrogate. I'm going to return IR, just because I want to write the entire thing out. It returns IR. And then from here, return IR. Then from here, it's going to return back IR all the way back to the starting point. Return IR over here. Return IR over here. Return IR back here. So it's going to unwind. So it's going to relay this string over and over again. So what's going to happen is in each function, sort of recursive function call, it calls running. So we're going to call that running function within that for loop that goes through all the neighbors of a node. So if it returns a blank string, then try a different neighbor. If it's not blank, okay, then just simply relay that string all the way back to the beginning. So what's going to happen now is we're back here in file storage. Let me go ahead and clear all this stuff out now. So now our depth first search returned all the way back. I'm going to clear all this up. This is a tedious process, but it's okay. It's better than erasing on a classroom whiteboard, I guess, so I still prefer this. So we came back to file storage, it returned IR. Okay, so we're going to go to that index IR of my keys array, and those two elements in there is going to contain winding corridor and operation room. So I'm going to actually insert this edge into my graph. And what's going to happen now is I'm going to then wipe this out. It's interrogation room in the in that keys hash map. I want to clear that vector inside of keys interrogation room. So I don't want, if I enter this room once again, I don't want to return back because now there's no key in this room anymore. So hopefully that keys hash map is, not confusing. So then, since in main it returned back interrogation room, it's not exit, we're going to restart that first search and we're going to pass interrogation room into that cur pointer. And we're going to again run that first search. So I'm going to kind of speed this up a little bit. So it would go ahead, it would try first search, would go here, then we go here, and just kind of pattern, L corridor. And this purple or this violet arrow is now part of my graph because we were able to open this door. We enter this room and oh, this room actually has a key. So it's going to return, I'm going to return OR all the way back to the calling function, OR for operation. I don't want to write the whole thing out, but operations room it would return. It returns a string. It's kind of silly how depth first search does it like this, but it returns OR all the way back. So, and then of course returns OR back to main. So when main calls a function, it returns OR. That means, okay, so we didn't find an exit, but we did find a path of some sort that we found a new room that could be opened. So we're going to now open up this room. So OR, operations room, has a key that opens up the door between main office and basement stairway. Then we're going to wipe this out in our keys vector, our keys hash map, like that. And then we're going to simply just call DFS. And since the function, so we're going to be back in main, obviously. So we're back in main, and the function returned operations room. So we're going to pass operations room into that cur value, into that cur parameter for our depth first search traversal. And we're going to explore. So now we're going to explore. And I guess just to make things simple, we go to winding corridor, then west stairway, I guess information office, main hall, payphone corridor, main office, and now we can actually go to basement stairway because this green sort of edge has now been added to my graph. We're here, and now we hit Watchman's room. So it's going to return WR, which is short for Watchman's room, returns that all the way back. It's going to relay that all the way back to main. It relays this all the way back over here. And it's going to relay it back to main as well. So then what happens in main, it returns the string Watchman's room. Awesome. So we're going to go to our keys at the keys of hash map. In the bracket, you will pass in Watchman's room. And we're going to get that vector out of that hash map. And the vector is going to store, obviously, dark room and exit. It's going to add that edge into my graph. And then I'm going to go ahead and from main, again, call this running function and pass in Watchman's room into my cur field. So it's going to basically start DFS from that node. Let me just go ahead and clear all this out. So we're going to now call DFS on, or is running on Watchman's room. And of course, what happens, it will just traverse through all of this. And then it found exit. So in your running function, you want to have a base case where if cur equals exit, then at that point, it's up to you what you want to do. But I return exit all the way back to main. I would relay exit all the way back to main just to be consistent. And then in main, if exit is returned, then you break out of that loop because you're going to be in a loop. You're going to call DFS in the loop in main. If it returns exit, that means, okay, well, you're able to escape. You found an exit path. So that's going to be what you want to do. So let's go ahead now and go over a case where it's not going to lead to a winning move. So I have playthrough A and playthrough B, which are both winnable. Let's look at playthrough C. I think playthrough C is the one case I had that is actually not winnable. So I guess poor Leon in that case. So maybe somebody will help him, I guess. I don't know. So, oops, I put it here. So here's going to be this scenario. We have the same graph we're going to use, but now the keys are dispersed somewhere else. And this approach is going to actually lead to a non-winnable combination. Let's see how this is going to work out. I'm going to just put these all over here for right now. Maybe I actually should stop the video and restart it. just so I don't make a mistake and have to redo the entire walkthrough. So maybe I'll do that next. I'm going to erase this. Actually, I'm going to go ahead and stop the video right here. I'm going to restart it with the correct inputs or with the correct marks. That way, if I make a mistake, then I'll have to redo the entire video. So let's just go ahead and do a break, I guess, right here. Okay, so let's go ahead and just double check this file. So right here, it looks like, so file storage has a key that opens up winding corridor operations room, so pink. Then press room has a key that opens up main hall and payphone corridor, which is this blue right there. Watchman's room contains the key as dark room to exit. Operations room contains the key that opens up the main office and basement corridor. Okay, so awesome. So this is going to be our setup. As you can see right here, this will definitely lead to a loss. Let's see how depth first search approach will do this. So of course we start from our main hall initially first. I'm going to go a little quicker here just so I don't have to go to every redundant step. But let's suppose for now we're following depth first search in this order. And we find this room and there's a key in this room. So we're going to return FS all the way back. We're going to relay this all the way back like this. And return file storage back to main. So we're going to go ahead and of course we're going to wipe that key out, and we're going to add this edge into my graph because now we were able to find a new door I can open up that can, you know, go to that room. So we're going to go ahead and now we're going to call DFS on file storage because file storage was returned back to main. So we're going to use that return type and pass that into another DFS traversal and pass in file storage as our cur. Okay. So now let's suppose we do this kind of quickly. We're going to go here, and then we go to this room. And oh, we found the room that has a key. So we're going to return OR all the way back to main. We're going to relay this OR string through the returns of the function and return OR all the way back to main. So for OR, we're going to unmark this. We're going to add this edge into my graph. And then we're going to, of course, in main, call this function, this running function, but we're going to pass in operations room into that cur parameter. And here's where things will get interesting. So we're going to call DFS over here, call DFS here, call DFS here, call DFS here, call it here, call it here. It returns back an empty string because that path leads to a dead end. Okay, fine. That means we're gonna try a different path. We're gonna go over here. Then we're gonna go over here. It returns back empty string because exit is not actually open because remember we had to unlock the exit. We haven't unlocked it yet. Returns back an empty string. Okay, fine. So now from west stairway, we can't go anywhere else because we've already been to winding corridor. So return back an empty string. So information office, we tried both neighbors. They both returned empty strings. So okay, fine. Return empty string back over here. From main hall, we had nowhere else to go. Return back an empty string. From waiting room, nowhere else to go. Return back empty string. L corridor, return back empty string. And then we go back to winding corridor. Return back empty string. And return an empty string back to main. So if main gets empty string, that means we know that we were not able to unlock any new doors, which means that we are stuck. If there's no doors can be unlocked, that means if you call DFS again, it's going to return the same results. I mean, we can't advance any further. We didn't find the exit. We found no new room. So, Leon, I'm sorry, but it looks like this playthrough C didn't really work out for you. So that's going to be how we analyze this. So you have to call DFS in a loop several times. Every time it returns a room, if it's not exit, we're going to add a new edge into our graph and then call DFS from that node that we were currently on. And then we're going to go ahead and call DFS again. So basically, in this example, the real problem is that the blue key happens to be right here, and it needs to open up this door. But in order to get to this, you have to open this door up first, which, as you can see here, that's impossibilities. That's kind of why this will lead to a failure. So that's basically how you want to think about this. So this is kind of a long video, I think, but at least, you know, maybe it kind of helped you see what's going on. And there's specifications, of course, as always. There's that. And in the sample run, basically you want to output these messages, essentially. So for part A and part B, then Leon can escape. And of course, you know, Leon has to go ahead and try to meet up with Ada and try to work together to escape Raccoon City. And if it can't escape, then I think part C will have this output. So yeah, so I guess you want to submit these files, and I guess the video would be linked right here once the video is done in the PDF, and that's that. So hopefully this video helped you understand the assignment. So I guess happy coding, and till next time.